All right, so proof by contradiction, it's an all-time favorite of mathematicians everywhere. Here's how you do it. You assume incorrectly that whatever you want to prove is true is actually false. Then you show that that assumption leads to mathematical nonsense. Then that means that your initial assumption was wrong, which then means that the thing that you assumed was false is actually true. You can pause the video and stop and think about what all that means, or you can just jump straight to this example and make a lot more sense. The first example here, prove that a quadrilateral has no more than one reflex angle. So a reflex angle is more than 180 degrees. So to prove by contradiction, the first thing that we do is assume the opposite. So assume a quadrilateral can have more than one reflex. That's our assumption. That's the opposite of what we're trying to prove in the first place. Now, if a quadrilateral did have more than one reflex angle, that means that those two angles together are each over 180 degrees. So put them together and you have something over 360 degrees. But the internal sum of the angles in a quadrilateral is only 360 degrees. So you've got four angles, two of which are reflex. So then we've got more than 360. There's a contradiction. There's mathematical nonsense. So if our initial assumption leads to mathematical nonsense, then therefore a quadrilateral must have no more than one reflex angle. So I'm not sort of talking about this one formally. I just want to give you the sense. Assume the opposite of what we were trying to prove in the first place. Wait for the nonsense to appear. And then obviously our assumption must have been wrong. Here's our second problem. Show that if three numbers, A, B, C, form a Pythagorean triple, they cannot all be odd numbers. All right, so if they're a Pythagorean triple, we can say that A squared plus B squared equals C squared. And before we get to doing that, we should probably make our wrong assumption. So assume they can all be odd. All right, so if we have A, B, and C and they're all odd, 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 what happens when you square an odd number? I'm not going to prove it, but when we square an odd number, we will also have odd, odd, and odd. You can prove that by direct proof if you want to, but take my word for it. Squaring an odd number gives you an odd number. Okay, but what's happening here? That's an odd number. We're adding it to another odd number. When you add two odd numbers together, you're supposed to get an even number. So an odd plus an odd cannot equal an odd. So we've got this contradiction happening here. Because an odd plus an odd, or because an odd squared number plus an odd squared number cannot equal an odd squared number, then our initial assumption must be wrong. They can't all be odd. So therefore, they can't be odd. We've proved it by contradiction. We assumed they were odd. Then we ended up with mathematical nonsense, so they must be odd. This one's the most famous of all proofs by contradictions. Prove root 2 is irrational. All right, so what's our first step for proof by contradiction? Assume pi on 2 is rational. Now remember, rational means it can be expressed as a fraction. So now I can say that root 2 equals p over q, where p and q are integers with no common factors. Because obviously if p and q had common factors, we wouldn't be doing p over q, we'd be doing p divided by whatever common factor they had over q divided by whatever common factor they had. So that's a ratio in its simplest form. Now if we get rid of the square root from the left-hand side by squaring both sides, we can say that 2 is equal to p squared over q squared, right? We're just squaring left and right. And we could also say that 2q squared is equal to p squared. All right, what does that mean? Well, that means that p squared, therefore p squared is even. Therefore, p is even. All right, and you can prove that, but we're not expected to prove that. That's sort of a number fact that we should know. All right, so interesting. We now know that p squared is even and p is even. If something's even, we can express it as like 2k. So we can say let p equal 2k, and we can then sub that into that equation there. I'm just going to change colors here. All right, so we can now say that 2q squared equals 2k squared, which means that 2q squared equals 4k squared. All right, we're getting close. This is a beautiful proof. So we've got q squared is equal to 4k squared over 2, right? So just dividing that by 2. And we can now say that q squared is equal to 2k squared. What does that mean? Well, if q squared is equal to 2 times something, that means that therefore q squared is even. Therefore q is even. Uh-oh. This is where the contradiction comes in. P is even. Q is even. But our first assumption was that P and Q did not have common factors. But if P is even and Q is even, they do have common factors. The common factor is obviously 2. So summing up, P is even, Q is even, but they shouldn't have common factors. Contradiction. Therefore, root 2 is irrational. Okay, this is definitely one of the prettiest proofs out there. You should really stop and admire this proof for a moment. Also, according to legend, Pythagoras got so annoyed about this proof that he threw some guy off his boat and he drowned. So it's got a special part in mathematical history. This one's kind of similar. Suppose x satisfies 5 to the x equals 2. Show that x is irrational. So obviously if we want to show that x is irrational, we should assume it's rational. Assume x is rational. All right, so if we assume x is rational, we can let x equal p over q. So it feels similar to the last one, right? 5 to the power of p over q equals 2. Now, if I raise these both to the power of q, I'll get 5 to the power of q to the power of q equals 2 to the q. That's going to be, so those q's are going to cancel each other out. I end up with 5 to the p equals 2 to the q. Now, it's not immediately apparent why this should be a problem, right? Well, maybe I should have made sure that I said something special about these p's and q's. No common factors, obviously, because it's a simplified fraction. Now let's look again here. 5 to the p. Well, 5 to the 1 is 5, 5 to the 2 is 25, 5 to the 3 is 125. They've all got 5 on the end. They're all odd, right? What about this one? 2 to the q. 2, 4, 8, 16, 32, 64. They're all even. But right here, I'm saying that 5 to the p equals 2 to the q, but they obviously can't ever equal each other. Contradiction. So if there's a contradiction here, it must be because my assumption was wrong. Therefore, x is irrational. a nice, neat little, quite quick proof there. All right, that's enough of that. Time for you to get to work. Simply a matter of practice and just getting stuck in and having a crack.